Welcome, everyone. Welcome to this webinar. Super pumped up that you're all here. I know there's more that's going to be joining. Tonight, we're going to be diving into some of my favorite conversations, diving into TX valves. And we're going to be diving into A2L refrigerant TX valves. A lot of you have been hearing about A2Ls out there. They are, we consistently see more units coming in both the residential, light commercial applications. All my friends out in Europe that I talk to, A2L is not new out there. We're seeing it now. So why we're doing this is we want to teach you some tips and tricks on TX valves. I do tons and tons of supermarket trainings, refrigeration trainings, and I think really bringing the experts like Jamie here tonight to talk about TX valves. We're going to get into tonight installing, sizing, setting up TX valves, because this is super important as a technician. It's so important because if you don't set up a TXV properly, you don't install it properly, you can run into a world of hurt. And I see it time and time again. I used to be a technician in the field, and I going into service jobs, and I remember talking with the service manager like, Trevor, can you just help me talk with my technicians to stop adjusting the TX valve? Because a lot of the times it's something else in the system if the TX valve is set up. But the first step is sizing it correctly, which we're going to talk about tonight. We're going to talk about installing it properly, setting it up, and troubleshooting. I'm here with my good friend Jamie Kitchen from Danfoss. He's been there for a long time. We've seen each other tons of events over the years when I used to work with a manufacturer, and then we meet each other at tons of training events. Now he's still continuing to put up the good fight and train and educate the people across the industry, from wholesalers, technicians, manufacturers. Jamie, I'm super excited about this.
Yeah.
Let's get a conversation going, brother.
For sure.
Why don't you do a quick introduction to yourself, Jamie?
All right. Well, as you say, Jamie Kitchen. I'm a technical person that pretends to be an account manager, salesperson. Joined Danfoss back in '99. Previous to that, I worked setting up the refrigeration lab, training lab at Humber College. Worked off and on the tools, did some work on centrifugal compressors, doing teardown classes, doing teardowns on the weekend, things like that. Most of it was really big stuff. So moving into commercial refrigeration and air conditioning when I joined Danfoss, that was a different story, because now it's much more compact, a lot different way to approach things. And so was a training manager at Danfoss for quite a while. Now I'm responsible for what we would call the indirect sales, aftermarket. And wholesale sales is pretty much training, because unless somebody's comfortable with your product, they ain't going to buy it. And unless it's installed properly, they're not going to like it, right? So all of these things you really got to deal with and make sure that people are comfortable going forward and understanding what's happening. And then we're all happy, right? The end user's happy. The customer's customer, and Danfoss is happy. That's just the way it works, but it needs to be done right.
Yeah. And I think what you said there, it's all about training. That's what we do here at Refrigeration Mentor. That's what Jamie does consistently, is training. And that's why you guys are all here, is to learn something. One of the big things is I've been doing and a lot of you know me that are here. I do tons of CO2 training, tons of natural refrigerant training, but I've been getting so many requests on A2Ls lately because there is a lot of things up in the air. You know what I mean? With regulations, leak mitigation, and these are new words that you're going to start to hear about. Maybe not regulation, but like leak mitigation is something very important to understand. And this affects all parts of the industry: residential, light commercial, and large ones. So you as a technician out there need to understand working with an A2L. If you've been doing it properly, me and Jamie talked about this earlier, if you've been doing it properly from day one, your install properly, using inner gas, brazing properly, having leak detection, all this stuff.
Yeah.
Using A2L is not going to be a big deal. Just like I talk with people about R29. What is the biggest misconception that you see right now, Jamie, with A2Ls? Because there is a fear factor there, because we hear flammable, mildly flammable. But what are some of the things and misconceptions that you may have seen over the last couple of years? Because this is not new for us. We've been hearing about this for 4 or 5, 6 years. You know what I mean? Like a long time. Maybe not that many, but definitely 5 years for me.
Yeah.
But what are some
again, all you need to do is go on one of the subreddits, on Reddit or something like that, and read through the comments and read through some of the forums and that. And there's information spreads like crazy, and people remember it, right? And they always remember the thing that scares them. And so, to be honest with you, you hit the nail on the head. I remember we used to do R290 training classes when True and Refrigerant and these other guys started to switch from R134A to R290 because the efficiency is like 30% jump, right? 25% jump in efficiency. It was fabulous, fabulous. But the issue was it's flammable. And let's face it, propane is flammable. Yep. And so there was a lot of misconception, a lot of concern there. But when you walk them through the process, it's just like you say, if you're doing all the right things anyways, you're using inert gas, you're not just, pulling the refrigerant out until you have 4 PSI in there and then putting your torch on and things like that. If you're not doing those kinds of things, you're probably not going to run into a whole lot of issues, especially with the smaller refrigerant charges. Now, A2Ls, they're not nearly as flammable as, say, isobutane or propane. Like, in other words, the amount of mixture that you need, say, refrigerant mass for a given space volume is many times larger. And the good thing about it is that it allows us to add pounds or kilograms of refrigerant charge to a system to get larger systems. But it also means that a small leak, right, unless you're in a perfect storm where it's leaking into a small space and you happen to have the perfect mixture, nothing's going to happen, right? That's not an issue. We dealt with this with R290. If the refrigerant vents into the space, it's safe. If it vents into the controlled environment, like inside the fridge, now you got a problem. We can design around that. And the protocols for servicing equipment, as you mentioned, inert gas, making sure you have proper ventilation, none of this stuff is rocket science. Follow best practices and you'll have the best results. Simple as that. I mean, some of the things you read, you think we're using highly enriched uranium or something like that, the way they're talking about some of this stuff. Yeah. Don't let it go critical. It's crazy, but I can understand people's fears. But what cracks me up is I have people that work on 575 volt equipment. No problem. No problem, right? It'll kill you quicker than a lightning strike, right? A2Ls, though, whoa, that's really scary, right? If you understand something and you know about it and you work with it, those fears disappear, but it just seems to be the unknown. And so it always stayed with me that, with what I'm looking for, like the opposites where you could be acceptable and understand something and be comfortable with something that's far more dangerous than something that you don't understand, which you're far more afraid of.
Yeah, and I totally agree with that because I see so many, I meet so many technicians in all our different training programs that they come in. It's like, man, I didn't know how to work on R290 or CO2, but then I took some training and then I actually went and put my hands on it. And I actually went and did it myself and I followed the proper practices and you know what? It worked. And just like you said earlier, True, other manufacturers back in 2013, 2012, 2014, were building this equipment. And I know for sure, I'd love to see in the audience, like thumbs up, who has worked on R290 already. Just throw it in the hands, or A2L, put your thumbs up in attendees. And also, I would love to find out where everybody's from in the chat. Where are you dialing in from right now?
Yeah, exactly.
We want to find out where you're from. I love this. Look at all the people who's worked on this already. And we got a good training happening right now. We're going to dive in. So the first thing that I think we're going to talk about a little bit, some of the differences about newer refrigerants. We know they have to be a blend on these newer A2Ls. They're a mix of different gas to get down what we call GWP, global warming potential. And why are we doing this? Because what is happening is that our planet's starting to rise up, the temperature's starting to rise, and this is only one thing factor. Refrigerants, depending on how they're made and designed, they have a global warming potential factor. And so now what refrigerant manufacturers had to do, and like a lot of other industry, not only refrigerants, they have to reduce that global warming factor. So 404, for example, was almost 3,900, almost 4,000 GWP. 410 is like 2,000 or 2,100 GWP. Now in the rules and regulations, it has to be below 700 GWP, 300 GWP, 150 GWP, depending on the application. Now, it could be commercial refrigeration, could be residential, could be chillers. You know what I mean? You're going to want to have to dive into that. But we're having blends of refrigerant. What does that really mean, Jamie, when we're now starting to deal with blends of refrigerants, which is not
Well,
new?
yeah, I mean, it's that part's really hasn't changed. All refrigerants were blends. I mean, R12 was chlorofluoromethane and R22 was chlorodifluoromethane. These are all compounds mixed together. What a blend means is you take one of these compounds and you mix it with some other compounds. And some of these compounds, when you mix them all together, say 410A or 404A or whatever, they will act like a single refrigerant, say, for example, and they will boil off at a given rate. Things are fine. You don't see a lot of glide. Whereas some of these other blends almost act like you just took a bunch of different refrigerants and poured them in. And I don't want to use the word auto cascade, but if you know what that means, you'll understand where I'm going. The different refrigerants boil off at different rates. And so that's what gives you your glide. Because when you first go into your evaporator, a specific refrigerant is going to boil off faster than the remaining ones. And then the next one boils off, the next one boils off, and this affects your temperature and pressure. We call that glide. From a calculation standpoint, working with a refrigerant blend that acts like a single compound is much easier for a lot of people because we're used to that. We're used to 22. We're used to, say 404A or 410A. Well, you don't have to really worry about it. That was one of the things that challenged people with 407C, where all of a sudden you had this refrigerant with glide. And again, it threw an extra set of calculations in there that if you got wrong, substantially impacted the performance of the system. And so people were cognizant of that. But that's what these blends mean. So keep in mind that 410A, 32, 454B, these aren't brand new compounds or brand new things that we created from scratch. We just took some of this, and some of this and mixed it together. Guess what? All of those refrigerants are in all the other refrigerants as well. They're just different mixtures of things that we've been using. And so nothing is really new. It's just kind of wrapped all together differently. And when you do that, you end up with a different set of characteristics. This one boils at this temperature, this one boils at this temperature, and you can mix and match to make what you want. Now, does that mean it's going to be a great refrigerant, or is it going to solve your problems, or is it going to be a great air conditioning refrigerant and refrigeration refrigerant? Probably not, right? The laws of physics don't change. But the laboratories can mix and match to make a lot of different things, right? And so this is where we are today.
Yeah. And that's so important because when we dive into something, where we're going to dive in right now, is into superheat, right? So when you have a blend, it's different than when you're doing a single refrigerant. So when you had R22, it's a single blend refrigerant.
Yeah.
So that really means that your dew point and your bubble point are the same on your pressure temperature scale. But when we get into what Jamie was just talking about in blends where they boil off at different temperatures, that's where you got a different temperature, bubble point, and dew point.
Mm-hmm. And we can go into that after this because it'll be fresh in your mind.
Yeah.
But I stuck with R134A here. We were thinking of upgrading it. You can go with 513 if you don't like R134A. But essentially, this is what you're going to see in a lot of fridges. If your fridge is more than, 5, 6, 7 years old or whatever it is, this was the refrigerant of choice. This replaced R12 back in the day, and so on. So what you're seeing here, when you're calculating superheat essentially tells you one thing, and that tells you how much refrigerant you have, mass, if you want to call it that, how much refrigerant mass you have compared to your load, right? If you have less refrigerant compared to your load, it means you're going to run out of liquid sooner in your circuit, which means you have 100% vapor. Now that vapor now has more highway, more time to pick up heat, because remember, you're probably blowing in a medium temp refrigeration system, 12, 15 degrees above, maybe 20 degrees above your refrigerant temperature. You're going to pick up some heat. And so the longer you have where you're a vapor, the more heat you pick up. The issue is vapor does not really pick up any heat. 99 or 95% or whatever of the heat absorbed in your evaporator is by the liquid. So you want to make sure you have just enough liquid, not too much, not too little, kind of like the Goldilocks zone, right? Because remember, an evaporator is not static. Your humidity increases. You throw a bunch of stuff in there. You open the door. You stare in there, not knowing what you want. All of these things can suddenly throw a load or change your airflow on your coil. If you're right on the corner of having liquid leaving and you suddenly drop your heat load by 5 or 8%, now you got a river or whatever of liquid heading to your compressor. Nobody wants that, right? So that's where your TXV, being an adaptable control, comes into play there. So if you measure the pressure in the system and convert that to saturation temperature, you'll end up with a value. In this case, 8 or 20 degrees Fahrenheit. That means the refrigerant is changing state. So since we're adding heat, it is boiling off. Now remember, it doesn't matter the temperature or pressure. If the refrigerant is warmer than the air, it's going to condense. Doesn't matter what the pressure or temperature is. If it's warmer than the surroundings around it, it's going to give up heat and condense. If it's cooler, it's going to absorb heat, right? One of the first things you learn in thermodynamics. So in this case, it is cooler than the air. We're absorbing heat, so we're changing state. And then once we run out of liquid, now that 20-degree refrigerant, 100% vapor, is going to start to warm up and superheat. If you want to know what a superheated vapor looks like, look around you. The atmosphere is superheated. Steam, when it's superheated, is clear. Gases like refrigerant and that are clear when they're superheated. So if you see steam, it is not superheated. If you can see it, it's not superheated.
Very interesting. Very interesting. And the big thing is that you need to know how to do this. This is a check that is overlooked and overmissed. People go in and look, oh man, I got bubbles in the sight glass, or there's something wrong with the system. I got to add gas or something to it. And they didn't even check superheat, or they check superheat and the superheat's off. And it's like, I got to adjust the TX valve, and we'll dive into that. That's not what.
Don't touch the TX valve, man, please.
Don't touch it.
Unless somebody was monkeying with it before you.
Yeah.
You don't want to be that person, right? Yeah. Because if it's not the problem and you monkey with it, now you've got two variables, right? One you created yourself and one you haven't figured out yet. And two variables, as you remember from high school, is a lot harder to solve than one.
Yeah. And the big thing is that you got to do all your checks first. And we'll get into the troubleshooting too. You got to make sure that coil's clean, the fans are running, the filter's not blocked. There's so many different things that we need to check before we just start.
And we can walk you through and tell you the difference.
Yeah, it's so important. Well, let's dive into subcooling now. So subcooling is another important thing.
Yeah, probably even more so nowadays with adaptive controls. So subcooling in a condenser is a little bit different because basically going into your evaporator, you're at what's called saturation. So you go through your metering device and it expands. And some of your liquid flashes to vapor, and I'm not going to go into the details why, but it's pretty much locking up the excess energy that's in the liquid. That's what creates your vapor. Coming out of your compressor, you don't have liquid. If you do, you got bigger problems. Trust me on this one. So you've got dry superheated vapor coming out of your compressor. So when it goes into the condenser, the first thing it does is, I don't know, what do we call it? De-superheat. It cools down sensibly. Like I'm going to use the word de-superheat. I just created it. So it's going to de-superheat, and the temperature is going to drop. And it's going to drop to the point where, if you look in this case here, it gets to the point where if you cool it down anymore, it's got all this pressure pushing against it. And if you cool it down anymore, it hasn't got enough energy to stay a vapor. So the pressure starts to push it together and it starts to form a liquid. And as you remove heat from it by basically rejecting heat to the air or water, it condenses and condenses and condenses until you end up with 100% liquid. Now your latent heat exchange is stopped and you have 100% liquid. And because that liquid is still warmer than the air, you're going to start to subcool. The more subcooling you have, the more the temperature has dropped below the point that it has condensed. So if you want a good picture of what subcooling is, think about this. All right. Water boils at 100 degrees C, 212 Fahrenheit for our American friends at places where most people live, right? If you live up in Tibet and you're 10,000 feet above sea level, this doesn't apply to you. All right. when you turn the hot water tap on and it comes out at, say, 60 degrees Celsius or 160 Fahrenheit, right? You want it good and hot to get rid of Legionella. Water boils at 212. If it's coming out of the tap at 160, subtract those two, you have 52 degrees of subcooling in your water. So you have to add 52 degrees in your kettle before it starts to boil again. So that's kind of how this whole thing works. Now, remember, this is important. From an efficiency standpoint, you are emptying the bucket in your condenser, and that is the same bucket you're going to fill in your evaporator. So the amount of heat that you can absorb in your evaporator, the amount of cooling you're going to do, is to fill that bucket up. So you have to go back to your condenser and empty it. So the subcooling is a way of further emptying that bucket so that when you go to your evaporator, you have more room to fill it up. Remember, 100% of the heat you're going to reject occurs in the evaporator, or occurs in the condenser. So the energy in your liquid coming out of the condenser is the same as going into your metering device, is the same as going into your evaporator. Because remember, there's no energy change BTU per pound wise in your TXV or your metering device. So subcooling is not just for eliminating flash gas, it also helps make the system more efficient.
Yeah. And it's so important to understand that. And then sometimes you can't check it at the condenser perfectly, right? So you gotta sometimes you gotta get the pressure from a different place. But getting the temperature at the outlet, checking your subcooling at the outlet of the condenser, and checking your subcooling. So I meant at the inlet of the TX valve. You want to know what the temperature at your TX valve is as well in system. So checking your subcooling there is important as well. But a lot of times you don't have the pressure port at the inlet.
And I hate checking liquid pressure. Even in college, man, I remember I was with a guy that burned all the skin off between his fingers, right? On the outdoor condenser. I just don't like it. I don't know what it is. It's one of those things that's always bugged me. You got to do it, but and there's a way to do it. And if you had never taken liquid before, man, you might want to get taught how to do it first. But not a fan of doing it, but you have to, right?
Okay, so I did update this slide, and I threw 454B because this is an A2L, and we're kind of talking about their valve tonight. So let's just go into, this is the Danfoss Ref Tools app. I recommend download it. I use it in a lot of my trainings. It's pretty easy to use. So if you're in bar and Celsius, great. You can do it in bar and Celsius. You can do it absolute. So if you want to change into PSI, you just go up here, change the PSI.
Change it to PSI in Fahrenheit. I want to show something here.
So we change it PSI in Fahrenheit.
Yeah. Okay, so make it like go down to a saturation temperature. No, do 410A. Go down to a saturation temp or 404A, but do a saturation temperature, say of do 100 degrees saturation temperature. Okay. So what I want you to do is see where it says "do" at the top there. Click that button. Okay. So with 404A, you have 0.6 degrees of glide. So essentially nothing, right? Go to 410A. If you can. By the way, this search thing here works great.
Oh, yeah, it's beautiful.
Same thing. So 98. So put that in. So 100 degrees. Again, check it, right? What do you got? 0.2 degrees of change.
0.2.
Now, go to 454B.
Let's leave it on absolute. Yeah.
Sorry. You do 454B. All right, so 100. So look at that pressure there. Oh, yeah, man. Now, hit that. So you got about 2.2 degrees of glide. Is that a big deal? No. Would it make a big difference down the road? No, but you have to be aware of it. Now, remember, you use your dew point, right, for checking superheat. You use your bubble point for checking subcooling. I don't expect anybody to remember that, right?
That's okay. But that's important because when we go to a refrigerant, say like 448 now.
Oof, not my favorite refrigerant, but we have it.
Well, watch this. You got 100 in absolute, and then you a bubble point, and then it's 108 in dew. So there's
and that's enough, right, to make a difference. So the point here is that as long as you know what you have, remember, information, knowledge is power, right?
Yeah.
follow the steps, follow what the recommendation is. Okay, again, I even had to write it down. Dew point is superheat. Use your dew point value for superheat. Use your bubble point for subcooling.
Yeah.
As long as you know that, if you have access to that information, you are golden, right? You can have confidence in what you're saying. All right. So my point here is that use these tools to get the information. And once you have that, use those in your calculation, and you can be a lot more comfortable going on, right? It beats, right, listening to the flack that you have. I'm not saying you don't get some good information online, but it can be confusing sometimes because people will contradict each other and things like that. So the manufacturers, the refrigerant people, whatever you need, use the tools they have and have confidence in that.
And I just want to point out to everyone, I did make a mistake in the slide. This was still 410. So you see, if we do 454B at 110, that would be
so about 20 pounds left.
365. So you got to, especially if you're using digital gauges, you got to make sure that you put the right refrigerant in. So I just want to show that.
And remember, people, A, B, and C make a big difference. Yeah, we showed you 454B and it had 2.2 degrees of.
Yeah, I want to show that. Watch.
Of glide. Go to 454A and see what happens.
Try 455. Watch this. This is amazing. I love this. So if we do 100 again, like we were doing before, and then we go into.
No, you have to do 450. Yes, look at that.
Oh, 17. Man. 17. So make sure you use your dew point.
That's your temperature difference, practically, man.
Yeah, it's crazy. It's crazy. Okay. So we talked about superheat, subcool. Let's talk about the principles of the TX.
All right.
And my good buddy Matt Wax, way to go, bud. In the chat, he was like duperheat, superheat, duperheat. I guess that's lots of people do. So perfect. Let's get into operation principles. Let's talk about that because this is important as well. This is how you really got to understand a TX valve, right?
When I first grasped this, to be honest with you, it made a huge difference for me. In not so much, I would say, as a technician, but when I'm trying to understand how something works and troubleshoot it when I'm on the phone, when you're at a job, because when you're on the phone and people are explaining to you, you're not there. If I was there and I would know exactly what to look at, I would know all the things I need to do. But when somebody's trying to explain something to you, you're trying to picture it in your head. And being able to visualize the forces on things like TXVs, for example, help you understand what's going on. Because they're giving you numbers, they're giving you values. You have to be able to plug those into a model in your head and understand what's going on, right, to visualize it. So there's 3 forces in a TXV. There's 2 closing forces. One is the evaporator. So the TXV feeds into the evaporator. All right. So if you look at a TXV, it's got an arrow on it on the side. That's your primary flow direction for what you want to use it. So on the outlet where that arrow is pointed, that's your evaporator. So even though the refrigerant's flowing out of there, it is at the pressure going into the evaporator. It could be before your distributor. It could be if there's no distributor, and we'll talk about that in a second. But that's the force under the diaphragm that sits in that power head. That's one. Second one is your spring pressure. It is there to make sure the refrigerant leaving the evaporator is warmer than its changing state at. Okay. And that is what we call superheat. So the amount of force that spring puts in, remember, pressure is equivalent to temperature. So if we think of that spring pressure as additional pressure underneath, that's equal to temperature. So if it pushes hard enough to equal 6 degrees or 7 degrees, guess what? That's what we would call static superheat. That means or some people call it factory superheat. That's the amount of superheat you need for the valve to start opening. That's not what it's going to regulate at. That's what you require to start compressing that spring. So 2 closing forces. The opening force is your bulb pressure. So inside your bulb, you have a secret sauce, right? You have a mixture of gases, refrigerants, things like that. You might have some carbon in there to control the release and how fast it absorbs, opens and closes, whatever. But those are the 3 forces. So when you adjust superheat, what you're doing is you're compressing that spring or you're releasing it. And that means the amount of temperature difference between the bulb and the evaporator is either going to need to increase or decrease to match that.
Yeah. And the way I think about it too, because you got to see, I don't know if the next slide. Oh yeah. So
there you go.
diving into this is what's really important. You got to understand there's different valves out there. There's conventionals, there's valve ports, there's automatic, there's all these different valves, but most of the ones
automatic expansion valves. Oh my goodness, man. I haven't heard those in a while.
The main ones though today that you see is balance port. Like that's the one that you'll see the most on standard systems like AC systems.
It's a catchword that you have today, and it definitely has an importance for certain things. Absolutely.
Yeah, there's lots that don't, like on small, you still got cap tubes and things like that. But when you have a huge tonnage where there's a lot of load changing and stuff like that, you're going to see something that's balanced port.
If you got fan cycling, you definitely need something like a balanced port, right? And so that's something that you'll see a lot of times.
Yeah. The way I look at it and I think about it is that that bulb, like you said, is the opening force. If I squeeze, so right up here, and there's refrigerant and there's cross charges, and like you said, there's slow releases, fast releases. If it's pressure limiting valve, there's lots of different ones out there. But if you grab it and hold it and you increase the pressure, what does that do to you increase the temperature of the bulb? What does it do to the pressure? Increase temperature, you increase pressure. And so what that does, it pushes that gas, it forces that gas and pushes down on this diaphragm to push on the pin, to open it up. And like Jamie says, you take that spring and down at the bottom and you tighten up that string and there's like a little plate. I don't know what you call that.
I call it a pressure plate, but yeah.
The pressure plate. So that's on the spring. And now we're pushing up against that pin. So we're fighting the diaphragm, not fighting, but we're trying to match that.
Yeah, they're trying to find a balance. So it's always trying to find what we call an equilibrium, which is a fancy term for saying that things don't really change much.
Yeah. And the big thing is, if that is something, one of those are out of the whack, if you don't have any refrigerant in that bulb, that we're not going to open, you know what I mean? We got no opening force. If we have something jammed in it because you didn't use inert gas and now I'm getting carbon stuck in there, it could be jammed open or it could be.
Keep in mind, these are moving parts, man, and they're small. Like you can easily draw blood with the valve stem, the valve seat on some of these smaller TXVs. They're that small. So it doesn't take much to plug these up.
Yeah. No, it's important. So that's kind of how I think about it, because it's important to visualize inside. And actually, you got to take some of these apart. The ones that you can take apart, pull them apart so you can learn inside.
Especially with the orifice in that. If you take that orifice out and you see that screen is plugged, guess what? That's a pretty good indication of what's going on, right? So why didn't the filter dryer grab that stuff? Right. Yeah. Well, was the filter dryer 30 feet away and there's a whole bunch of braze marks on the line between it and the valve? I've seen it.
Oh, yeah.
Right. Make sure. Why not move that filter dryer closer to your expansion valve? It's not like it's going to break. Right. Or it needs to be kept a certain distance apart. You know, it just, and of course, you know, if there's crap in the system on your TXV, there's probably more crap in the system that can let go too. So.
Yeah. The big thing is there's so many DOA TX valves out there, right? And then
we get them all the time, and I got some good pictures, man. I'll tell you.
I've seen them.
I'll tell you.
I used to send a ton of them back to the manufacturers in Germany, so we'd send them back, and every time here in Canada, we're a division of them, they would be like, denied, and then they would send these pictures, and they would just show this little bit of debris in there that was contamination, and it's like that's what jammed it up. And I talked to all the valve manufacturers, like I know all of them, even when I would work for a manufacturers, and it's the same thing. All these valves come back, they're overheated a lot of times. I think the average max on most of them around 250 Fahrenheit, I think about I think it's like 120 or 107.
It depends on what they have for, like if you look at the top of the valve, that diaphragm is what we call tool steel. Basically it is tempered steel. And so if you heat it up, you're going to take that temper out of it. If you take that temper out of it, it is going to fail. Usually where it connects to the sides of the power element, right? Because it cycles literally thousands of times an hour. It's pulsating, right? It's not just sitting constant. And so over that life, if you take that temper out of it, it's going to fail, right? And you're looking at a dead TXV. And so little things like this, you got to be careful. Now, brazing in an expansion valve is not something you can just do like this, right? It takes practice. It takes a talented torch a lot of times because they can be a miserable thing to braze in, these big brass body valves. If you got the extended ends, fantastic. Otherwise, you're wrapping this thing with wet wrap, with paste and that, and it's a fight against time to get it in because it's trying to evaporate the heat you're applying, and you're trying to heat it up before it overheats, right? So,
Yeah.
not fun.
I've been yeah, you got to practice this stuff. So if you work
100%.
at work at a contractor, get some soft copper. So soft copper, learn how to swedge, get a swedge tool, swedge it so you don't have to buy fittings because that costs more money, but you can swedge it, put things in and practice brazing. This is how you get better. You got to wrap this stuff. You can't just, I've met so many people, I've seen people do it. I don't need to wrap the TX valve. We just burn it in right quick. First, that's the way you overheat it. And I was at one site one time. I can't remember how many years ago, 5 or 6 years ago. And guy was brazing in the TX valve, didn't wrap it. And I see the whole bottom fall right out onto the ground. The whole bottom, like this whole bottom here, not on a Danfoss, a different valve, but
you can put that back in, no problem. Yeah. I know if somebody said that to me, I'm sorry, but I'd be standing there staring and there'd be crickets in the background, like one of those TV scenes, where it's like, seriously, dude, like, but I've seen pictures. We used to have the wholesaler send us back pictures, and you just wonder, like, I would never have the gall to bring this in for warranty if it looked like that. But
yeah. So, but this happens. I've done it, guys. I've brazed in TX valves without wrapping them. You know what I mean? So I'm just telling you got to wrap that stuff, and it takes long. I just wanted to ask you one question. All the TX Danfoss ones that I installed back in the day, I used to use silver solder, and I noticed there looks like kind of copper in here. Do you need
you basically just use standard Silfoss because the copper stops on the inside.
Okay.
And one of the tricks I do when you're doing a demo is I put it in a little stand. I just get some black iron pipe and just fasten it down, and it sits right in there. I braze it right in with just a MAP gas hand torch, and I pick it up. Okay. But the trick is you got to heat the pipe up before the valve, because the only part of the valve you're heating up is just that end. So point the heat away from the torch, heat the pipe up first. It'll heat up in a few seconds. Once it starts to turn cherry, back it up, put your Silfoss on, away you go. Do not use flux, because the chloride in the flux will actually make pinholes in the valve.
Was your old valves, though, like 15, 20 years ago, all stainless steel, and you guys changed to copper, or was it?
No, it's always been stainless steel body, cap tube, and sensing bulb. And we always had that bimetal connection just because it's just 10 times. I'm not saying we never had a stainless steel valve, but not a TXV that I'm aware of.
Okay, so because I used to use flux and 40% to install Danfoss.
Because they think it's dissimilar metal. And I still have people tell me that, and they don't believe me when I tell them otherwise. But hey, what do you want to know, right?
Well, I'm looking. That's why I asked, because I see copper in there, and I remember installing some Danfoss because I didn't do a lot of Danfoss. Just I did some, and I wanted to ask that question. So thank you for clarifying that. You just use regular 15 or whatever. Let's talk a little bit about internal and external.
All right. Okay, so go back to what we're talking about, the forces on a TXV. And so that evaporator pressure that's underneath that diaphragm and your spring pressure, that's what the sensing bulb needs to overcome. And again, if it's set for 7 degrees of superheat, 3.5 Kelvin or 4 Kelvin or whatever the heck it is, right? Or range, that is what's set. So as long as the pressure where the sensing bulb is pretty darn close to what the pressure is leaving the leaving the TXV going into the evaporator, right? On either end of the evaporator, let's put it that way, inlet and outlet. As long as they're pretty close, no problem. You can use an internal equalized TXV. All right. And these are like small single circuit evaporators. The overriding factor is you do not have a refrigerant distributor. If you have a distributor, now you've got a whole set of differences here. Almost all air conditioning that I've ever seen, at least that I remember, has a multi-circuited coil for efficiency. Larger refrigeration systems have a multi-circuited evaporator. Don't think just because you have a piston or a cap tube that it's single circuit. It's not, right? Remember all the old piston air conditioning systems out there. There's still some of them there. They're all multi-circuited. If you have a distributor, you absolutely 100% need to use an external equalized valve, because here's why. Remember that pressure under the evaporator? If you did not have that external equalized valve, if it was internal equalized, your TXV would think the pressure in the evaporator is what it is before the distributor. And that distributor might have a 15, 20, 25 pound pressure drop across it. It needs to, because it has to equally distribute all that refrigerant, hopefully equally. All right. And so what ends up happening is the saturation temperature or the actual temperature in your evaporator could be 10, 15 degrees less than what the TXV thinks it is. Okay. So if the TXV thinks it's 45 degrees and it's actually 35 degrees because of the pressure drop through the distributor, and if your sensing bulb needs 7 degrees of superheat to open, again, if what I say, it thought it was 45 and 35. So if the TXV thinks it's 45 degrees, it needs 7 degrees of superheat. That's 52 degrees. But if it's only 35 degrees in there, it's going to need 17 degrees of superheat to open up. And so you're drastically going to underfeed the evaporator. So remember, whatever the temperature equivalent of the pressure drop through your distributor is, and through the evaporator, whatever the temperature equivalent of that pressure drop is, you will add that to the superheat opening requirement. So the bigger the pressure drop, the more superheat is going to be required at the sensing bulb to open it. And again, you're always going to underfeed that evaporator. So the rule is you can use an external equalized TXV even if you don't need it, but you can never use an internal equalized one if you need an external equalized one. In other words, if you have a distributor, you need an external equalized one. And remember, even if you don't need that external equalization connection, you still need to connect it to the evaporator. Don't plug it off, otherwise it'll never open. Okay, so make sure you do. Oh, I've seen it. Oh, look at that nice cap on there. I think I found your problem.
Yeah.
Make sure you do that.
Yeah, definitely. That's huge. If you, just add it, right? If you don't have another valve and it's
done it myself, man.
And it's an internal, just add the line, drill a hole in it, make sure you don't get any copper in the line. The big thing is that these can plug up if you don't, once again, use nitrogen while you're brazing. So you got to purge, because these can plug up. And now if you plug these up, two things can happen. I've seen it both ways. This is the one of the closing forces. So now if you don't have a closing force, you could flood it. But if it plugs up, you also could get refrigerant in this line, which puts a lot of pressure underneath here. And it could also force it close. So I've seen both, you know what I mean? Because I've read a lot of literature where people said it'll only flood if it's plugged or not. But we don't know if there's refrigerant under here heated up. So just be aware. Could be one of those. What's your experience on that, Jamie?
To be honest with you, I can't single it out. I've seen them where they have mounted the external equalization line on the bottom. It's almost like they're trying to drain oil from the system.
Oh, fill it up with oil.
I've seen that before. And generally what ends up happening is the TXVs are unresponsive. And I can't remember now if it was open or closed.
Yeah.
All right. All I remember was I could never find the person responsible for doing it.
Yeah.
So, but I think we're just all so amazed by your AutoCAD quality hand drawings that you're doing here, man. So
this is a Venturi distributor, like Jamie said, which is a lower pressure drop. I think it's 15 PSI, 20, depending on the manufacturer. And then you have the orifice type, which would go in right here, which you put the block of orifice and it'll be a hole in there. And these can be up to 35 PSI, 20 to 35 PSI, depending the size of the hole. So that's something you got to be aware of. That's something you got to be aware of. Let's keep going.
Now, on the bigger systems, you're never going to find an internal equalized.
No.
If you can show me an internal equalized 20-ton TXV, man, I'd be pretty impressed. So it's generally on the sub 3-4 ton kind of area. And definitely once you get below 1.5, 2 tons, you're going to start to see internal equalized valves.
Want to dive into operating superheat a little bit?
Yeah, okay. So the thing about the sensing bulb, the charge in the sensing bulb, is it's not just refrigerant. And so just like how we had glide and refrigerants, you can mix and match the components, the gases, whatever you want to call it, in the sensing bulb to kind of work on the profile of opening and closing. Do you want it to open with very little superheat at low temp? Do you want to open slow, close fast? All of these things can be done. But essentially, when you think about it, as the load on the evaporator increases, your superheat increases, sensing bulb increases in temperature. That's going to drive the pressure on the diaphragm down. And the reason this extra pressure is required is because when you compress a spring, it pushes back. So the harder you push it, the harder it's going to push back until it's fully compressed. And so a lot of times what you'll see, and again, you can kind of flatten this out. There's all kinds of things you can do. But generally speaking, if you're under high load, so think we can either do a walk-in box or we can do a dwelling or whatever. But think you have a room that has a certain load. A whole bunch of people start moving around in there and people give off latent and sensible heat. There's equipment in there firing up, whatever. You increase the heat load on this evaporator. The TXV now is going to start to open up, but you will still see a slight increase in superheat. It's not going to be a lot, right? But it will be a slight change in superheat. And the idea being is that the most accurate part of the stroke for this TXV is between pretty much 0 and nominal load, right? And the nominal load is what the TXV is rated for. So if you buy a 1-ton TXV, that is your nominal load. What most people don't realize is TXVs will give you 20, 30, 40% more capacity than what they're rated at. But you see how that line kind of bends over at the top? That means that the superheat opening relationship of the valve, superheat capacity, is no longer that accurate. It's not linear anymore. And so you're going to start to see your superheat rapidly increase compared to the amount the valve opens up. But we can call that a pull down load if you want. So what happens is that TXV is going to open up and it's going to feed that evaporator as much refrigerant as that compressor can take, right? And your evaporator pressure is going to go up. Your saturation temperature is going to go up. Because if you have a fixed speed compressor, what's the only way to put more refrigerant through it? And that is for the density of the refrigerant to increase into your suction line. So your pressure and temperature need to go up. So if you're good, you can actually tell how much humidity is in a space just by looking at your evaporator pressure and your TXV superheat, right? Because those are the two main things in air conditioning that give you load, right? Is your latent heat. Remember when we look at setting superheat and subcooling, what's the indoor value we use? Wet bulb, right? It ain't dry bulb, it's wet bulb. So those are all indications that come together. So the most accurate stroke of this is between nominal load and down below. So what ends up happening is when the system first starts up, TXV is going to open up and you're going to start operating somewhere between nominal load, maybe above and maybe below. And as your load gets pulled down, the TXV is going to close until the space is satisfied, and then bang, it shuts off. And then it sits for a while, heat builds up, and then bang, it opens up again. It's going to open up, and then slowly it's going to come back down again. And so that's how the operating sequence works. Now, if you adjust superheat, you're not really tilting it. You're just sliding that graph this way, all right? And you may think, oh, man, if low superheat's so efficient, why don't we just dial this superheat down? Well, you can, but here's the problem. Every evaporator has what's called a minimum stable superheat curve. And see how that TXV's got a straight line? That minimum stable superheat is curved. And so if you put it too far, it's going to be inside that curve at one point, and you're going to start getting liquid shooting out. You might be measuring 3 or 4 degrees of superheat, but you got liquid going down the center of that pipe, and that's going to start the valve hunting. And so it becomes unstable. If you ever run into an unstable system like that and you've checked your subcooling, you have enough refrigerant charge, increase your superheat slightly until it stabilizes.
Love that.
Increases another 0.5 degree, and you're golden, man.
And you know, I had to learn that the hard way. I learned that there from electronic expansion valves. Because I didn't really know that with TX valves. But when I started training on electronic valves and I got to play around with them, the electronic valve's all over the place. It's hunting. And so then I just started raising the superheat, and then all of a sudden it was perfect. And then I'm like, let me go try this on a TX valve. So then I went and tried to drop this load. And then all of a sudden you would see the valve just hunting because I had a bunch of monitors on it. Then I increased the superheat on the valve and it started to run perfectly. So if you ever have a lot of hunting and you made sure that it's not your fans, your condenser fans banging on, banging off, or your evaporator fans changing, or someone's opening the door, changing the load very quick and it's a stable load, the coils are clean, everything's running normal, and you got that happen. Increase that superheat just 1 degree, you know what I mean? And then another degree. And then all of a sudden you'll see that line start to stabilize. I love that. I love that. Great, Jamie. That's a great tip, man. Let's jump into a little bit more. We've been talking about troubleshooting the whole time, but let's jump into more troubleshooting tips.
So what I usually do, keep in mind that the class that I normally put on is quite a bit longer. But in order to properly troubleshoot, you can look at a form and you can say, is it this or is it this? And you can check the box off, and then you can be a robot if you want. But to do proper troubleshooting, you need to know, what would the system be doing if it was running correctly under these conditions? How much humidity you have? What's your temperature? How much load? Whatever. What's my voltage? All these things. If it was running correctly, what would I see? And then you compare that to what you see now, and that difference then is how you identify the problem. Okay? Yeah, you can tear that compressor apart and we'll tell you, or Copeland or Bitzer or somebody will tell you it overheated, it flooded, right? Whatever. But there's a lot of different things that can cause those same problems, right? You can have an oil issue due to temperature, due to low oil, due to no oil return, due to liquid return. All these things can cause, lubrication failure. So you need to be able to go through and be a detective, put your detective hat on and go through and look at the clues. So airflow, big deal. So if you happen to have, let's say, proper airflow, I shouldn't say high airflow, let's say proper airflow. All right, it's an air conditioning system. You're running at 47 degrees. I show 16 degrees of superheat. You may say, hey, that's a lot of superheat. Not really. If you have a lot of humidity in the air, right, that can drive your superheat up. That just tells you that valve is throttled open. All right, and you'll see that superheat start to drop. 15, 14, 13, whatever. Now remember, superheat in air conditioning is not the same as superheat in refrigeration, because you got a 35, 40 degree temperature difference between the air and the coil in air conditioning. You can afford to have a lot more superheat than you can in refrigeration. So everything's working perfectly. And then all of a sudden you get a dog or a cat, or you don't vacuum, or somebody puts some boxes in front of all your return airs or something like that, right? Or you never heard of an air filter before in your life. And suddenly your airflow is no longer good, right? Guess what? The TXV is going to do exactly what it's supposed to do. When your load on your evaporator drops because of poor airflow, it's going to start throttling closed. Now remember, the only way for the compressor pumping to balance the TXV is for that evaporator pressure to drop as well, because that reduces the pumping capacity of the compressor until it matches the lower feed rate of your TXV. So look at this, 39 degrees, right? You may think, holy crap, I'm undercharged. No, you're not. Look at your superheat, 9 degrees. That's a reflection of how open your TXV is. So your TXV is opened a lot under good airflow, high load, perfect. It is less on low load. So I would start looking for an airflow issue, or maybe you've got your differential on your thermostat set to 12 degrees or something like that, and it's running for 2 weeks straight. Who knows, right? But basically, you need to figure something out there on what's going on.
Yeah, I like what you said earlier. Like in the last slide, you said you want to understand the system, how it runs normally. And I do this in all my trainings. It doesn't matter if it's supermarket, if it's chillers, if it's just HVAC or compressors. You got to go troubleshoot a system that's running normally.
Mm-hmm.
That's what you got to do. And people are like, what do you mean troubleshoot a system? You go in, you get all the systems running fine, all the pressures, all the temperatures, all the voltage on every point, every electrical point. Well, why would I do that? That would take me a half an hour. So now you
have a half hour invested.
Now you know how it's supposed to be running. This is supposed to be 230 volts or 575 or 380, wherever you're at in the world. This is supposed to be this Celsius or Fahrenheit or PSI or bar. It doesn't matter. Write it all down, jot it all down, draw the picture out. Honestly, I've been training people for a long time. And when they started doing this, they're like, Trevor, I'm a way better troubleshooter. And I'm like, yeah.
And it's quicker too. You save a lot of time doing that, man. Trust me. You don't think you spend a lot of time doing stuff. You spend a lot more time doing things that aren't productive than you actually realize.
Chasing your tail. I've done that for years, so I know all about
Especially when you're tired and you get that tunnel vision. That's the worst, man.
Let's talk a little bit about low charge. What happens?
All right. So low charge is one of those things where you want to identify, is it low charge or is it low flow rate? So let me clarify this. So a proper charge, everything else is working properly. This is a walk-in cooler, right? It's got 20 degrees evaporator temp, could be 22, could be 24, whatever, medium temp. You got 12 degrees of superheat. She's chugging along. It's got some load on it. Your condenser subcooling, right? Whoops. What happened here? There we go. 12 degrees. Maybe it's a bit high, right? Maybe it's supposed to be 10, 8. But the point is you have a solid column of liquid leaving your condenser or close to it. So if you've got good subcooling, you ain't got a refrigerant charge. That is not an issue. You have enough refrigerant in the system, right? If you take those same measurements and your evaporator temperature goes down and your superheat goes in the opposite direction, goes up, that means you don't have enough refrigerant in your evaporator. It doesn't tell you you're low on charge. It just tells you you don't have enough refrigerant in your evaporator. But you know what does tell you if you have enough charge or not? Is the subcooling on your condenser. So if your subcooling on your condenser is like 0 or 1 degree or 2 degrees or something, you're low on charge. And so the expectation is you don't have enough subcooling to maintain a column of liquid in your liquid line. How do you expect your TXV to work with that tiny little opening and you're trying to shove vapor through it, right? Not going to work. And so it'll also be unstable a lot of times. You'll see it going up and down. You see this a lot of times when people are charging AC systems and they don't put enough refrigerant charge in, you'll see it hunt. And you hear the guys at the wholesaler on the tech phone. And as soon as they hear that, the first thing they'll say is, you got enough charge in there? Well, I think so. Well, what do you mean you think so? What did you charge it to, right? There's a value that you charge that to. So these are the things you got to remember. When you're looking at superheat and evaporator temperature, you're only looking at the evaporator. You're taking a snapshot of what's going on in the evaporator. That just tells you don't have enough refrigerant in the evaporator for your load. That's the first thing I mentioned when I mentioned superheat. Subcooling, on the other hand, that takes place way over there in your condenser. That determines your charge. All right. Yeah. For an adaptive device, you mentioned EEV and TXV. Those are two adaptive devices that we're talking about here.
Yeah. And the big thing is that you got to make sure that condenser fans are running, the condenser's clean, you know what I mean?
Yeah.
And, you can't condense.
Yeah. You know what's happening right now is all the supermarket guys are going, oh, somebody hold my beer. Because when I said, 1 or 2 degrees of subcooling, if you don't have a load on your systems and all your liquids sitting out in your condenser, right, somewhere, it's not uncommon for you to have very low turnover in your receiver. Your subcooling is going to be low, right? And it's a pain because when you need to suddenly feed all these meter devices and you don't have any subcooling, it's going to grind its way there until it does, right? And so these are the issues. It's not uncommon to see really crappy subcooling in some of these, remote multi-circuited systems. But for what we're dealing with here, it is absolutely a good indicator.
Yeah. And here's a little bit of low charge. You wanted to go through that, or I think you covered a lot of that.
Yeah, we can definitely go through low charge, undercharged. Definitely. Let's go to the next one here. Oh, sorry. Go back. I'm sorry.
Yeah. So that's the first one. This is low.
Yeah. Next one. All right. So let's again compare low airflow and undercharged. In a low airflow, low load situation with a TXV, the evaporator pressure and superheat both go in together. They move in the same direction, right? Because remember that diagram of the TXV? As your load goes up, your superheat slightly increases. So as long as your evaporator pressure temperature, and superheat are moving in the same direction, that is a load-induced or load-reliant change that an adaptive device like a TXV is going to do. All right. Your subcooling will also change a little bit. It can go down as your load drops because guess what, people? Do you know what determines the amount of subcooling you have? It's one thing, and that is the temperature difference between the refrigerant and whatever it is you're dumping heat into. So guess what? A bigger condenser, it doesn't give you more subcooling. It gives you less because it allows your approach temperature between the air and the refrigerant to get smaller. That means you're going to save a boatload of energy because your compression ratio is going to be smaller, but your subcooling is going to be less. So remember, if you're charging a SEER 13 system and you're charging to a given outdoor ambient and wet bulb temperature, and you're used to doing 13 degrees of subcooling, and you go to a SEER 17 system, you ain't charging to 13 degrees of subcool anymore. You're probably charging to 8 or 9, right? And so if you charge it to 13, you just overcharge that system, and they just drop 2, probably maybe 3 SEER points, right? And they're not going to get the money out of it. So congratulations, right? Make sure there's no rule of thumb to follow here. Make sure you follow those guidelines.
Yeah. And one thing I like, because I didn't do a lot of residential and stuff, but I worked on some, is that most manufacturers slap it right on the side.
Yeah, you can't miss it.
Subcooling. Here is the superheat. That's it. That make it so easy because I installed a few before in my day, and it's just that you know what I mean. Depending on the ambient condition, there's a little chart there. Follow the instructions.
I remember at Humber, we used to send the students out with the sling psychrometers. Man, there was casualties everywhere, man, because these guys were like dealing with like nunchucks, right? Guys were getting chipped teeth and they were getting broken. It was hilarious, but they basically learned to take in that whole wet bulb scenario and learn what it was.
Yeah, no, exactly. So,
all right,
valves.
Yeah. So what you see here is just pictures that we take through this thing called a stereoscopic microscope, right? It just means you look through both eyes, and a bunch of account managers. Right. We're not people to sit and do nothing because that's just our personality traits. And so if you put a toy like a stereoscopic microscope, we're going to play with it. And, we're always shoving stuff under there to look at it. But these are the images that we take during teardowns. So when you send a TXV in, and it's usually a manufacturer, if you get a bunch of blockages, multiple ones, and there's a trend, we want to know, right? Because we want to be able to catch something. So what you can see here on the left, this kind of looks like salt, and that's exactly what it is. So as a manufacturer of compressors and components, and it doesn't matter if it's Carrier, anybody, or Danfoss, or Copeland, we're going to tell you refrigerant and oil. Because the reason we tell you that is because we don't have control over anything else, right? In a manufacturing setting, we can be all geeky and control everything. But once it leaves our hands, we no longer have that control over what people do, right? And so what ends up happening is if you put a bit of acid neutralizer in, fine. We got no problem with that. But if you put 5 times as much as what you're supposed to have in there, now you're going to have an issue because it's going to start reacting with things and you're going to produce some salt. And these can basically start causing problems. And it doesn't take much before you plug that TXV up. So again, this stuff works. Leak stop stuff works, right? Well, at least it used to work on my radiator in my Dodge Charger.
I don't know. Mine only lasted for like 6 months when I did it to a car in Australia. So I don't know.
Australia. That's because it's like 185 degrees outside. That's right. The soft solder starting to melt. All right.
I have so many people that reach out to me online. It's like, oh, I got this magic stuff to throw in your system. You're going to get 30-40% more efficient on our R22 system.
Oh, yeah? What law of thermodynamics did you follow, man?
I'm not sure what's happening. It's going to clean it all up. It's going to make it magic again. It's going to take that 1990 keep right that I have out there and turn it into the 2023 one or 2023.
Yeah, no, it's not. So funny. But that's okay. All right. So this is an argument that I have. I should say an argument because there's no wrong or right. All right. As a manufacturer, not of the equipment, but of the valve itself, we're always going to wimp out and say, follow the manufacturer's recommendation because we really don't have anything else to say. But if you ask for our recommendation on best practices, we're going to tell you to insulate that sensing bulb because it only makes sense, right? Yeah. Think about the sensing bulb. It's sitting on a pipe and there's only a little tiny bit of it touching that pipe. The rest of it is wide open to the air, right? And so that surrounding air, especially if it's moving, is going to have a large influence on it. So it doesn't take much of a temperature difference to cause that.
It's the same temperature. It's the same temperature, Jamie. That's a,
yeah, oh yeah, okay, yeah, always the same temperature. Yeah, there's no temperature for it. So I really don't care whose bulb strap you use, as long as it's metallic. All right. If it conducts electricity, it conducts heat. I'm not telling you to test that out, right? But remember that, okay? It does. So make sure it is strapped to the pipe. Don't crush the pipe, but it should take a lot of effort to move that sensing bulb because you don't want anything underneath it, right? Yeah. That could cause that. Next thing is to wrap the insulation around it, okay? Zip ties and duct tape is not a good 2-in-1, all right? Make sure you use a metal bulb strap, it's tight, and insulate it, because on a properly operating system like that, half the heat or more that goes in the sensing bulb doesn't come from the pipe itself. It comes from the sensing bulb, or the bulb strap that's wrapped around the entire pipe and over top of the entire sensing bulb. And it conducts heat and it's insulated. So you have this heat train then that conducts from the pipe up into the bulb. That makes it far more reactive and efficient. If you want to increase the amount of superheat that you have for destabilizing the TXV, if you want it to happen at 5 degrees instead of 3, just loosen that TXV up a little bit, and it will become unstable a lot quicker than it does if it's properly mounted and insulated. And this, by the way, you can mount it vertical too if you want.
Yeah.
Just make sure the cap tube is pointing straight up.
Yeah. And you know, I had that question a lot, like, I didn't know. And I looked at so many different manufacturers' valves and their literature, and not many people talk about it too much. But if you point it with and some people say, because you pointing it down, what could happen, Jamie?
Well, again, if you have liquid in there, it is going to migrate, right? It's simple as that. It's going to migrate, and you can basically cause it to become very sluggish, not react, denser, all kinds of things.
Heavier.
Yeah.
Might, you know what I mean?
Yeah.
So it could go down and on top of your diaphragm, pushing.
It sounds silly because, come on, man. That's an old wise tale. The liquid's going to leak out of the bulb. Well, it does, right? So it's just because of the temperature differences and things like that. And people say, hey, do you put it at 9 o'clock or 12 o'clock or whatever? And a lot of people don't like my answer, but it's simple as put it where there's not going to be any oil. All right. So when you put your coffee cup on your dashboard and you do the old movie scene of going around the corner fast, right? Your coffee cup goes towards the outside of the turn, right? Laws of physics. Your oil is going to do the same thing on a bend. So if you look at that bend there, it's going to shoot to the outside after the header. It's going to shoot to the outside of that bend, and then it's going to shoot to the outside of the bend down at the bottom of that suction line there, okay, leaving the evaporator. So put the sensing bulb opposite of that. If you don't have a bend, put it at 9 or 3 o'clock if you can, right? Somewhere in that area. You're trying to avoid the meniscus at the bottom, which is just the surface tension of the oil that has a natural reaction to go upwards. Okay, the smaller the pipe, the farther that oil is going to reach up. But again, use your head, right? Where is that oil going to be sitting? If it's on the bottom of the pipe, fine. Don't put it there. Okay. It's it because I've had guys argue. It's like guys that argue over, 0.1 inch of static per 100 feet or something like that, right? There's no fixed and fast rule.
Yeah. The big thing is when I started doing electronic valves, all of a sudden the bulb needs to be insulated. And then like in refrigeration, the air temperature is the same temperature. Well, no, the pipe temperature is not the same temperature as the air temperature.
No, it's not. If it was, you wouldn't have a heat transfer.
But it's close enough, I guess.
It is. Yeah, okay, fair enough. And again,
I don't think
if the system works, if the manufacturer doesn't insulate the bulb and they have a reason for that, don't insulate the bulb, man. It's as simple as that, right? But at least make sure it's still snug on there. Okay.
Yeah. Let's I want to thank everyone for taking the time and watching and staying here. So I put in a chat. If you got to get going, you can.
Sorry about that. I probably talked too much.
No, let's keep going. We're going to keep going. We'll probably do another 10, 15 minutes if you're okay with that, Jamie.
Yeah, sure. Absolutely.
The big thing is that if you guys want to go and rewatch it, I'll put on the on-demand recording. So let's talk a little bit about valve capacity, because that's pretty important as well.
Yeah. So when you're sizing something, a lot of times, okay, let's back up here. if I were to take, say, a second year class in college, and you were to say, what happens when the load increases on your evaporator? And maybe you've heard the story before. They'll put their hand up, and if they have the TXV, they'll say, oh, the superheat increases, the bulb pressure increases, the TXV opens up and puts more refrigerant in the evaporator. And it's correct, right? However, if I ask them what happens next, they can't answer that probably because they do not see it from a system-wide standpoint. Whatever that TXV does, it isn't in a vacuum, right? If it puts more refrigerant into the evaporator, the compressor then has to pump more refrigerant. That's adding more energy to the system. And so your entire balance then gets thrown off. So the idea of sizing equipment basically comes down to what condition ideally do you want this system to run at? Is it 2110? I mean, there's always going to be some variables, but you have to pick a certain point to size it at. And then once you have that point, now you select the components based on capacity so that they will be very close or as close as possible in capacity at the conditions you want it to run at. And this is very important because we use standard conditions to select equipment so that we can compare apples to apples between everybody. Because you can make something perform any way you want as long as you mix and match the conditions, right? So you have a standard. So if you're selecting it for a freezer or a cooler, for dehumidification, for sensible only, you size it based on those conditions so that when you throw it all together, hopefully not from across the street, right, it is going to work together and function as it should. Now, if your evaporator's too big, will it still work? Sure. But it's not going to work at the conditions you want, and you're not going to get the dehumidification or lack of dehumidification that you want, right? The worst thing with TXVs is undersized. If they're oversized, even 20, 30%, it ain't going to matter. They're going to throttle down no matter what anyways. They'll throttle down to 50, 40% capacity, right? No problem. As long as they're installed correctly and all the other stuff we talked about. So if it's undersized, when are you going to see this? Well, a good example of this is something that can't increase, something that can't adapt. So take your home fridge. It is designed to handle a fixed load, right? You're supposed to put stuff in there that's already cold. It's the same as a walk-in box, right? It's not designed for pull down. So if you put a 24 beer in your fridge, it ain't going to be cold in 5 minutes. It's going to take hours and hours and hours. We've all learned that the hard way, right? At a party.
Oh, man.
All right.
Get R12 and spray it in the bucket.
Yeah, absolutely. So the same with a TXV. If you have a normal load and it's not too high, that undersized TXV, it might do okay. You're not going to see, you might see slightly longer pull downs, maybe slightly higher superheat, but nobody knows what the superheat's supposed to be anyways half the time, so it doesn't matter. However, if you put product in there that taxes the load, in other words, it increases your load, now you're going to have a problem. You're not going to be able to pull that down. It's going to run forever. You're not going to meet pull down. And if you happen to be in a food scenario where you're data logging the temperature of the product, now you're going to have alarms everywhere, right? And now you're going to be in a problem because that product has stayed warm for too long, and it no longer has any value, right? So these are the things that make them stand out, right? So when are you going to see an undersized TXV? Unless it's drastically undersized, you're going to see it generally when you put a load on the system. Or you size it for a cooler and you use it in a freezer. So remember, nominal capacity is good for replacing like for like. So if you have a nominal 1-ton valve and you replace it with a nominal 1-ton valve, as long as the first one was sized correctly, you're good. But if you have a 1-ton unit cooler evaporator in an ice cream freezer at -20, that nominal 1-ton valve is going to give you half a ton.
Yeah.
And if you need 1 ton, you're going to be grossly undersized. So remember, we get lazy a little bit in air conditioning because you don't get that much of a temperature range, 42, 40, 46, 45, whatever. But it's not -10, right? Because you don't cool your house down to 40 degrees. At least not.
And you've done so much training with wholesalers, contractors over the decades. You know what I mean? I've done tons of wholesaler training, contractor training, and I've seen so many wrongly size TX valves. What are some tips for the technicians and the people that are on here? What is the information they need to properly size? Because there's a lot of good softwares out there, but what do they need to size these TX
Make
valves?
sure you put the conditions you want. So if it's a -20, you pay attention to that. So we all make guides. All right. Here's our TXV selection chart. You've usually got nominal capacity, and then you've got the refrigerant and your evaporator temperatures. So find the refrigerant, find your evaporator temperature, and you go down there until you see the first capacity that's equal to or larger than your evaporator capacity. Easiest way to start, or whatever your load is. People always say load, it makes me nervous. But if you tell me your evaporator capacity, I can tell you the right TXV for that evaporator, right? Yeah. Whether you selected it or not correctly or not, I have no idea, but I can match that pretty easily.
Yeah. And then go into the softwares, ask people, because this is important, because if you're a technician in the field, a lot of times I see people just relying on the wholesaler, but sometimes the wholesaler doesn't know. You know what I mean?
So we all make mistakes. Engineers make mistakes. Manufacturers make mistakes. And one of the easiest and biggest mistake or most common mistake is what I just explained here. Nominal capacity versus application capacity. Yeah. Again, if one of the mistakes I see who people are not used to refrigeration, and I think it's hard, is because of that evaporator temperature difference that trips them up. Yeah. And we've all made that mistake.
Yeah. And I've seen it before too, where from the manufacturer, it was the wrong valve. So the back pressure was super high, right? Like in a super high back pressure or suction pressure. Some people say back suction pressure. It's really high because it couldn't, that the orifice was too small in it. So
it's amazing how that works if you're going to underfeed. But always remember, never assume that what's in there is correct. If you're doing a service call, people, you're in there for a reason. They didn't call you in there because they like you and they want to split a bottle of bourbon with you. You're there because there's a problem with the system. Okay. So make sure you verify the stuff that's in there, because it could be a very easy thing to fix, right? Sure, pulling an orifice out of a TXV or replacing a TXV can be a pain, but at least you know what the problem is, right? Yeah. Before you add refrigerant charge and you start changing this and you start changing, find out what the problem is.
Yeah, totally.
All right. It's now time for upstream obstructions. Yeah. All right. This kind of falls under, there's not the TXV. So electrical, think back in tech school, high school, right? You got 24 volts or probably 26 volts at your control transformer. You got 0 volts at your relay coil. And there's supposed to be voltage there. What do? You figure out where the voltage went, right? So you hopscotch until you see that voltage differential that tells you something is open, all right? So why is it then that when you have 0 subcooling at your metering device, you don't check your TXV, you just dump more refrigerant in? Can you imagine if people did that electrical? Oh, I got 0 volts at my relay. I'm going to put 2 transformers in now to supply power, right? Without ever checking it. Nobody'd ever do that, but we do it with refrigerant. So if you have flash gas at your TXV, in other words, you take that measurement, the TXV is hunting, find out where that subcooling went. If you've got subcooling at your condenser outlet, find out where it went. Usually, it's not hard to find. You can walk by a solenoid valve and it's squealing like a banshee because it is either stuck part way or it's plugged or something. Your filter dryer looks like somebody sprayed the end of it with that fake Christmas snow, frost. You basically have 2 metering devices in a row, right? And so never add refrigerant until you verify all of these parts upstream and you check your subcooling at your condenser. Then you can add refrigerant charge.
Yeah, and I like that. I had a guy take my supermarket academy and he did commercial HVAC for a long time. Then he got into supermarket refrigeration. He watched this one video. Over the weekend, he did the whole program, but he was like, Trevor, he messaged me. He's like, Trevor, I watched your video. My lead technician went into the store and he changed the TX valve and he did this and that. And I got called out to that store. And I watched one of your videos where he said to take the 2 temperature probes and put it across all the components. Not only there was a check valve and there was a filter dryer. So he went across the filter dryer. It was totally fine. It was the same temperature on both sides. He went across the check valve, a 7-degree differential across a temperature across the check valve. So he pumped it down, cut out the check valve, just cut it out, put a line in, worked beautifully. He was so pumped up, and it was just taking your temperature probes, and there shouldn't be a temperature drop across. That means there's a restriction. There's
at least he was smart not to stop at the filter dryer, because I'll be the first to admit I blame the filter dryer for a lot of things that get plugged, because that's what they're there for, right? To trap that stuff.
Yeah.
Now keep in mind, the pressure drop through a filter dryer, get this, are you ready now, is determined by the connection size, not the volume size. So you can have a 16 cubic inch dryer, and if you put a certain capacity through it, you're going to have twice the pressure drop with a 3/8 inch connection as you will with a half. In other words, that 16 cubic inch dryer can have twice the flow through it with the same pressure drop with a 1/2 inch connection compared to 3/8. The size of the dryer determines the weight of refrigerant charge you can dry before it becomes saturated. So the pressure drop is determined by the connection size. So if your filter dryer is plugged, and trust me, when we size these things, unless you're way, way off, it's usually sized for 1 PSI or 1.5 at the most, usually less than that. So if you're measuring a 2 or 3 degree temperature difference across your dryer, right? And unless the connection is like stepped down 2 sizes, that ain't the problem. It's plugged.
Yeah.
Now, whether it's plugged bad enough to want you to change it out, that's your call. Just remember, it's never going to get better, right? So, maybe sometime when the system's down, change it, make a note, whatever. But again, that's just up to you. It's never going to get better.
Yeah. We got a question here. Jamie, are you seeing damage with bioflow dryers and the valve plates with more air source or geo applications and guys changing more TXVs due to this? Do you understand that question?
I would say no.
Okay.
The only thing that can affect them is the rate at which heat transfer occurs and water and pressure changes. I do know in the early days of the pulse width modulated valves, the EVs, they're like a solenoid valve that opens and closes. Okay. And the amount of time it's open compared to the amount of time it's closed over a given period of time determines your capacity. They can create a pressure wave in the refrigerant line. And if you put your dryer too close sometimes, that pressure wave can cause the connection to crack. But those are old valve styles, and they've largely been replaced with the ones that don't pulse as much. But that was something we learned the hard way, right? Little things like that. But with a stepper drive motor or a TXV, maybe I'm reading this wrong or hearing it wrong, but I've never really known any issues that they would get plugged unless the people that are doing the install and that aren't keeping the system clean or something, but that's caused anywhere.
Seeing damage with bioflow dryers. I don't know that answer.
So biflow dryer,
it
just means it is used in a heat pump and it's got a baffle in it so that the refrigerant flows in it. It allows it to flow both ways so you don't backflow. So, your pool filter, if you run the water back to clean it out, it dumps all the crap out. That's what would happen with a regular dryer if you tried to back it up, right? You just put all the crap back in the system again. So they do have those baffles in them, those veins. How they could be affected, I don't know. But that's what that usually means, at least from my experience.
Good. Here's the last couple of tips we're going to give you. And I think adjusting superheat, this is super important because if you don't adjust it at the right time after certain conditions and you leave, you could be run into a massive issue. Because I've done this before. I've set superheat. I'm like,
the guilt's setting in,
and I'm gone. And then I come back and I'm like, oh my God, why is it so white?
Why? What happened? Well, there's a couple of good things here, and we'll start with the TXVs I'm familiar with. If you turn the stem clockwise, you are compressing that spring. So you're increasing superheat, which means the bulb temperature needs to have a greater temperature difference between the evaporator and itself in order for the valve to open up. You reverse it, you lower the superheat that the valve is going to start to open. Now, remember that point where I talked about the class that understood what happened when the TXV opened up, but they didn't really understand the rest of the system from a system standpoint? That's what you're basically doing. If you open the TXV or close it by decreasing or increasing the superheat, it takes time for it to work its way around. You will immediately see a change in the evaporator, instantaneous. As soon as you open or close that TXV, you're going to see a change, but it ain't going to stay there. It is going to fluctuate until the ripple, right, like in a pond, until that change in refrigerant balances itself out and it gets close to being to not hunting anymore. That's what we talk about when we say 10, 15 minutes. Now, it's also important not to be in too much of a hurry. So you are commissioning a system, you're starting it up, you're firing up the system. A lot of times there's going to be no product inside of this if it's a brand new build. And so what you're doing is slowly pulling it down. You don't want to pull down too quick because you don't want to mess up the concrete and everything, but you're slowly pulling it down. So what you're going to see is your superheat's going to go way up and then it's going to come down. Because remember, the mass of air that's inside that cooler is a fraction of the mass of the rest of the cooler itself and the floor and whatnot. So it's like if you're out in the woods and you go into a log cabin, you put the wood stove on, the air heats up. If you turn that cabin, that fireplace off, the temperature is going to plummet because the mass of the building is way more than the air. So the superheat's going to start moving. You don't want to adjust it when the superheat is moving because it's a moving target. Now, if you're not pulling down and the superheat stays high, then you can maybe adjust it and do it in steps, right, to get it down. But overall, what you want to do is let it go through a cycle. And once it gets close to being satisfied, pretty close to where it's going to kind of spend most of the time operating, right? Maybe above cut off a little bit. Then you can adjust it within that range and let it cycle through. But remember, it's very important to understand the rate of change of a TXV. We have a valve that we call the T2 valve. It's a brass body valve. It's got a stainless steel power head, cap tube, the whole 9 yards. It's been around forever. Its rate of change is 7, 8, or 9 degrees per turn. It is a very fast-acting refrigeration valve. Our TU valves, which is the stainless ones that you see, they're about 4 degrees. If you go to the TR6, which is our AC valve, it's about 1 to 1.5 degrees per turn. So a massive difference, right? Yeah. So make sure you understand the rate of change for this valve before you start dealing with it, or start off slow and see what happens. Because if you don't, you're either going to be sitting around all day wondering when something's going to happen, or all hell's going to break loose and you're going to wonder what happened, right? Because it's going to be fast acting. And so make sure you're prepared. Keep a note on the amount that you change it, the values, and the time. Because let's say you're decreasing superheat and the valve was stuck, and suddenly you've lowered the superheat enough that boom, whatever was causing the valve to stick flies open. And it wasn't a superheat issue. It was a valve stuck. Now you got to go back and put it to where it was, right? So if you know the number of turns you did in that, it's great. But if you don't, it can be a bit of a struggle. So make sure you keep your notes, because if something goes wrong and you got to defend what you did, it's much easier to say, here's what I did. Here's the time. It was fine when I left. This is what I saw, right? So
yeah, I love that. Taking notes and writing down how you did it and set it up. I know this takes longer, guys. This does take longer, but if you get in the habits of doing it, it'll just be normal. And then you're protecting yourself because now you can remember, because you do so many jobs or service calls, 5, 6 service calls a day. You can't remember what happened on Monday and that service call, that place that you don't even remember the name of the business sometimes, you know what I mean? So note and be detailed about this stuff, and it's just going to help you in the long run.
Yeah.
I really like that, right? Take your time with it. It does take some times, like when you're doing a lot of air conditioning installs, it's already, a lot of times it's set up from the manufacturer. So you don't have to play around with them too much, because they factory how many turns, they know the conditions and all that stuff. But when you get a dynamic
a lot
system,
of the TXVs aren't even superheat adjustable. Like if you look at the ones on ice machines and a lot of the residential, light commercial factory units, they've tuned those things in. And that can cause problems. That caused a lot of problems when we switched from pistons to TXV, and the industry grossly underestimated that the limited amount of knowledge there was on TXVs. People never seen them before. And if
Yeah.
it's doing something completely different than what you're used to and you can't adjust it, no wonder they're frustrated, right? So that's on us, right? You need to educate and train people to make sure that they're comfortable and they know what they're doing. So
yeah, and it's important to continue to learn. We're just sharing a little bit of knowledge tonight. Now you got to go out there and try this stuff, the things that we talked about, the install of it, the setting up of it, the troubleshooting of it, and what we talked about, because we can talk here all day and all night about what to do, but it's actually going out and taking that action and getting out there and actually checking the airflow and checking the temperature across it, checking the superheat, checking the subcooling, actually putting your gauge on the system and noting this stuff down. Like Jamie said earlier, troubleshooting a system that works totally fine. Understand all those checkpoints on whatever system you're working on. Jamie, this has been awesome. Why don't you talk a little bit about your e-learning platform where people can learn some more about Danfoss, because there's a ton of great training there.
Yeah, we have an e-learning platform, and a lot of times what you can do is you can log in, get to know it. It's kind of like a European thing. We probably make it a bit more complicated than it needs to be, but there's a lot of good material in there, and we're in the process of updating it. And so you're going to see a lot of good changes and things like that. So Danfoss e-learning, go in, learn everything from the basics to CO2 to ammonia, controllers, all kinds of stuff. It's like drinking from a fire hose a lot of times. There's a lot of information there. If you're interested in any kind of training whatsoever, reach out to Trevor, say, hey, I want to learn more about this stuff. He is absolutely a great portal to help go through. All right. Basically, as he says, get a conversation going. Listen, don't be the person that's afraid to ask the question. Knowledge is power. You're in an industry that's always going to need people to do what we do. It's pretty much AI proof, right? And it's a good living. So the more knowledge you know, the more power you have. So don't limit yourself by being afraid. Trust me, man. If you have a question and you can get an answer, that's a positive, right? Yeah. Don't make the same mistakes over and over again. So reach out and get the information you need.
And I love that, Jamie. I do a lot of trainings with a lot of like contractors, and you got senior guys and new guys. And the biggest thing is this is your career. This is your life.
Yeah, exactly.
If you're asking and you don't know how to superheat and you think, oh, it's a dumb question, and you think someone's going to talk down to you, don't worry about that stuff. Worry about your career. Then don't ever ask that person again. Don't feel dumb about, oh, I don't know how to check superheat. I've been doing this for 5 years. I've been there. I didn't ask the question. So it's so important. There's no dumb question in refrigeration. This is not a super easy industry. We got to know a lot. Like just a TX valve. We talked about an hour and a half now about TX valve, and that's just one component. There could be 50 components in a system. You know what I mean?
Yeah, exactly.
Just ask the question. I love that, Jamie. That was awesome.
One step at a time. Can I spend 2 seconds and just talk about one thing, the TR6 valve?
Yeah, no, let's do that. Let's talk.
Right. So not to pay the bills, but we kind of got to pay the bills here. We basically have what we call a universal aftermarket valve. And if we talked about the TR6 valve, we're introducing that for the wholesaler and for the contractor. And that's what you see here. So the valve has like the magic sauce in the bulb. It allows you to work with 32, 410A, and 454B all with one valve, right? So it services all three of those systems. It comes with Chatlift, AeroQuip, flare connections, comes with the waxing tape that's good for pulling the hair off your arm. It's supposed to be used for doing the sensing bulb installation, and it comes with the bulb strap. All you got to do is your refrigerant and your system capacity, and it's set up so that it's 1.5 to 3, 3.5 to 4 or 5. You pick your range of capacities on the side of the box, your refrigerant, and you're good to go. So it replaces multiple OEM valves with 1 or 2 or 3 codes. You can service any air conditioning system you see out there, right? And then on top of that, we have the legacy R22 407C. But think about it: 410A, 32, 454B, one valve.
David in the chat says he has TRX6s in his service truck right now for emergency repairs. Awesome.
Yeah, it's like those rescue motors used to have. The guys down in Florida and Texas and that deal with those, retirement villas and that, they love them because, again, it allows you to service all that equipment that you have. And in Southern U.S. is the air conditioning king of the world, right? I mean, here in Canada, we hope summer falls on the weekend, right? So we can go out and enjoy it.
Yeah, exactly. I love it. I love it. So, Jamie, how can people learn more about you, more about the TR6 valve? How can they get more information?
Basically, if you want, our guys, our sales guys, our account managers are out talking to wholesalers and whatnot. But essentially, if you want, you can reach out to me. But wholesalers are going to be having a lot of marketing campaigns and promos on for this. So go into your local wholesaler and say, hey, I want to know more about this Danfoss TR6 valve, because again, it is something that they should have on the shelf, because they're going to sell and they're going to be available everywhere, right? And they're going to be installed. Remember, if you look at the amount of TXVs since 2007, when SEER 13 hits, we have the majority of the market, Danfoss does, in those controls. So there's a good chance you're going to see a Danfoss valve. I see a lot of guys doing service videos and there's Danfoss valves in there. So you can replace anybody's valve with this. It's just 10 times easier. So, and again, you don't have to worry about picking or having a bunch of different valves on the shelf, because again, air conditioning allows you to have that flexibility.
Jamie,
I think that's it, man. Can you think of anything else?
No, I think this is beautiful. I've learned so much. I hope all of you learned out there. Once again, invest in yourself. Take the time. You did it here tonight and today, wherever you're at in the world, you're investing in yourself, and continue. Share this knowledge with other people. This is the only way you get better. Why me and Jamie know so much is because we keep sharing knowledge. We learn a little bit. We talk about it. We learn a little bit more. We share it. Yeah. We go out and actually do it as well.
Absolutely. And people, one thing, if I could just ask a favor of you, if you have been on the tools for a while and you know things, please be a mentor. Okay. And that doesn't mean telling people what to do, but take their questions seriously. All right. And treat them with some kindness, because remember, we all had to learn at one time. So if you have the knowledge and you've worked hard, please share it with others, because, hey, we'll all benefit from it, because the industry gets a better view from everybody, right? If we do things right.
Love it. I love it. Jamie, thank you so much again. Thank you everyone for sharing your knowledge in the chat, learning a little bit. As always, let's get a conversation going.